Hi, welcome once again to our Math as a Second Language workshop, where today there's a lecture I'm very excited to give. I hope you will be as excited, but at my age, I think it's very important that I be excited. I think you're going to enjoy this because this is the place where I think students start to feel that math is beyond them. They have to, remember, as you're learning arithmetic, they say the commutative property, the associative property, the distributive property, and after a while, kids are just memorizing these rules without really understanding why they're important. The amazing thing is you can use a rule without even know you were using it. I remember the story of the college freshman taking a literature course and was amazed to find out that he had been speaking prose his entire life. In other words, you have been using the associative, all these properties of arithmetic without even noticing it, perhaps. Let me show you an example. Okay, you called upon to add 234 plus 561. Okay, if you were teaching the course that we're doing now to youngsters, we wouldn't be using place value and the like, but since this is a course for you, I can assume you already know place value, arithmetic, and the like. All we're trying to do is to show a different way to internalize it, to make it more natural for students, etc. What does this really say? 234 written in place value is an abbreviation for 200 plus 30 plus 4. And 561 is an abbreviation for 500 plus 60 plus 1. So what we're told to do is to start with 200, add 30, then add 4, then add 500, then add 60, and then add 1. Is that what we do in real life? How do we teach the students to add? We say line the numbers up vertically. Numbers in the same column modify the same noun, whatever. 1 and 4 is 5, 6 and 3 is 9, 5 and 2 is 7. You write this down, that's the answer. What did you do here? Well, did you follow the directions? No, the first thing you did is you added the 1 and the 4. The next thing you did was you added the 60 and the 30. And then finally you added the 500 and the 200. You changed the order completely. But remember, if you view these as tally marks, nothing changes. In other words, no matter how you group them, you see, you can group these 4 with this 1, this 30 with this 60, this 200 with this 500, always stays the same. Okay? So this is the power of being able to visualize the tally marks. What rules did you use here? Nothing more than saying, I rearranged the tally marks so I could do it this way. So let's state the rules as they come up. The first rule is something called the closure for addition, closure property for addition. And it says the sum of two whole numbers is always a whole number. Now that may sound a little bit simplistic, like apples plus apples give you apples. Remember, we saw this in our previous lesson where an odd number plus an odd number was an even number. But why can we say that the sum of two whole numbers is always a whole number? Well, look at it in terms of tally marks. Here's 3 and here's 2. Can I squish these together? In other words, if I have a bunch of tally marks scattered all around, I can squeeze them all in together to form one simpler group, one bigger group. That's all the closure property says in terms of tally marks. The closure property for multiplication, pretty much the same thing. What does 3 times 5 mean? It means you have 3 groups of 5. 3 groups of 5. What does my fundamental property tell me? That the number of tally marks doesn't depend on how they're arranged. So I can push these 5 over, I can push these 5 over, and now what do I have? One group of 15. And I don't even have to know the name 15. I have this many. In other words, this many plus this many plus this many is this many. Okay? Next item I like to talk about is called the commutative property of addition. It says that when you add 2 numbers, the sum doesn't depend on the order in which you add them. And people say, well, what else would you expect? Well, in real life, order is important. I mean, I'm not going to pass judgment, but does it make a difference whether first you undress and then you shower? Or whether first you shower and then you undress? They're obviously not the same thing. And if order didn't make a difference, why should 3 minus 2 be different from 2 minus 3? Order in general does make a difference. Now, what happens is, in the old math, we would say 3 plus 2 equals 2 plus 3, because all you did was change the order. In the new math, we said 3 plus 2 equals 2 plus 3, because addition is commutative. And so you say, but what does commutative mean? Oh, it means you just change the order. Still doesn't tell you why it works. Why does it work for addition but not for subtraction? Why does it work for multiplication but not for division? Well, look at what this says in terms of tally marks. Isn't 3 plus 2 this many tally marks plus this many tally marks? And if I take these 2 tally marks and move them over to here, have I changed the number of tally marks? No, but now I have what? 2 plus 3. And if you think that this isn't confusing to students, ask them a question like this. Say, how much is 69 plus 2? If they know how to count, right away they'll say 69, 70, 71. They count on their fingers, and we tell them you shouldn't count on your fingers. Well, in a future lecture, I'm going to show you that counting on your fingers is wonderful, and you should do it all the time because it makes place value much easier. But that's for a later lecture. The point I'm driving at is, instead of asking the student how much is 69 plus 2, ask them how much 2 plus 69 is, and watch what happens when they try to count on their fingers. It's not self-evident to them that 2 plus 69 is the same as 69 plus 2. They tend to add in the order in which they hear the numbers. So with 69 plus 2, you start with the 69 and add 2, 70, 71. But with 2 plus 69, you start with 2 and don't have enough fingers. Okay? Well, that's all I want to say about that. Does the commutative property now seem simpler just by knowing that the number of tally marks doesn't depend on the order in which they are arranged? And the commutative property for multiplication works pretty much the same way. Why should 3 times 5 equal 5 times 3? And by the way, this is why I like to use square tiles instead of tally marks in dealing with youngsters, because it also brings up a geometry pattern. What this is really saying is a rectangle that's 5 units by 3 units has the same area as the rectangle that's 3 units by 5 units. In other words, if you stand this rectangle up on its edge, instead of having, see, let's take a look. Looking at it this way, here's 3 rows of 5. 3 rows, each with 5 tiles. Now, let's count by columns instead. 1 column, 2 columns, 3 columns, 4 columns, 5 columns. You have 5 columns, each with 3 tiles. But the number of tally marks doesn't depend on the order in which they're counted. So the 3 rows, each with 5, is the same number as the 5 columns, each with 3. Pretty easy to see from this point of view. And I think the picture itself locks into the student's mind. They may not know what the word commutative means, but they'll certainly know the concept. And I would introduce the proper vocabulary in a way that's user-friendly to the student, saying, look, you understand what it means that you can change the order in an addition and multiplication problem, but on tests, they're going to use a big word called the commutative property. So I want you to know that commutative is the grown-up word for saying all you did was change the order. See, the concept will register once they can see why it's important and where it came from. The associative property, it says when you're adding 3 numbers, it doesn't depend on the order in which you add them. In other words, it doesn't depend on voice inflection. I remember a long time ago reading a story in a weekly reader. I don't know if they still have the weekly reader, but it used to be something that students got every week in elementary school, and it would always start off with some kind of a joke. And one particular joke said, 2 men are talking, and one says to the other one, have you ever seen a man-eating shark? He says, no, but once in a restaurant, I saw a man eating tuna. Okay, same words, man eating a fish, man eating fish. That's okay, same wording, no way of telling which one is meant. Well, if you want a more serious problem, look at the phrase, this is called the associative property of addition we're talking about. Look at the phrase, the high school building. I deliberately didn't put any voice inflection in. Just by looking at this, can you see two completely different meanings? For example, is this a one-story building that holds grades 9 through 12? In other words, is it the high school building? Or is it a multi-story school building? See, by putting the hyphen here, high school becomes one word. Putting the hyphen here, school building becomes one word. But without the hyphen, you can't tell which of the two is being referred to. So the same thing might happen in math. Suppose you have 2 plus 3 plus 4. If I read it from left to right, I first add the 2 plus the 3, and then I add the 4. The parentheses take the place of the hyphen. This says everything inside the parentheses is one number. So this says you're taking 2 plus 3 and adding it to 4. This one says, no, let's go in the opposite direction. The 4 plus the 3 is one number. And so you have 4 plus 3 plus 2. In other words, these all look different. Well, look at it. In terms of tally marks, 2 plus 3 plus 4 looks like this. 2 tally marks plus 3 tally marks plus 4 tally marks. Well, can't I push these 3 closer to these 2? And now I have what? 2 plus 3 grouped together plus the 4. Or I could have pushed these 2 closer together, in which I would have had 2 plus 3 plus 4. Okay? You sort of get the idea what I'm driving at? All of these things can be done visually with no other axiom, that's a fancy word for rule of the game, no other axiom than the number of tally marks in a group doesn't depend on the order in which they're counted or in the order in which they are arranged. Now, to show you where sometimes you don't have associativity, is look at the expression 2 times 3 plus 4. If I read that from left to right, in other words, 2 times 3 is 6. See that one number? See, I'm reading from left to right. 2 times 3 is 6, plus 4 is 10. Now I read it from right to left. 4 plus 3 is 7. 7 times 2 is 14. They're not the same. In other words, this expression here is ambiguous. I need grouping symbols. And when I group it this way, this is called the distributive property. What's happening is you have a number multiplying the sum of 2 other numbers. And it's called the distributive property because the 2 distributes itself with the 3 and also with the 4. So it comes out to be 2 times 3 plus 2 times 4. Now, look at this in terms of tally marks. What is 2 times 3 plus 4? You have 2 rows, each with 3 plus 4 in them. Here's 3 and 4, okay? And I have 2 rows this way. So this is twice 3 plus 4. On the other hand, I can push these apart, and what do I see? I have 2 groups of 3 plus 2 groups of 4, okay? So, again, nothing new here. What am I illustrating here? Again, the power of these rules, how we use them all the time, and how easy they are to visualize if you use tally marks, square tiles, to introduce students to what's happening this way. And I think that's about a big enough chunk for today's lecture. So let me again close with our practice problem. And this again is kind of a subjective one. And just to have you see that not everything is associative. But here's the practice problem. Focusing on the word good, see if you can find 2 correct ways to interpret they don't know how good meat tastes. They don't know how good meat tastes. Focus on this question, pause the video, and then if you feel like it, come back, watch the rest of the lecture where I give you my interpretation of the solution, okay? Well, the idea is, when you say they don't know how good meat tastes, good can be used as an adjective modifying meat. In other words, they've only eaten bad meat, so they don't know how good meat tastes. Good can also be used as an adverb modifying taste. That is, they've never tasted meat at all, so they don't know how good meat tastes. Again, no way of looking at they don't know how good meat tastes without voice inflection to know which of the two meanings takes place there. So that's about all I want to say today. And what's interesting is these lectures that I've given so far, I consider very vital to the beginning of formal arithmetic, which usually starts with place value. In other words, place value didn't happen in a vacuum. It occurred very gradually, starting with these simple to easy to visualize properties. And in the next lesson, I want to discuss a little bit how what I call the chronicle of human endeavor. And I'll explain what that means in a bit more detail next time. And until next time, I hope all is well, and I will look forward to seeing you then.